Hello out there. This is Monique Morton, Math and Computer Science Director for AdvanceKentucky, and this is our newest episode of Office Hours. I hope all you AP Calculus BC students out there who are going to either watch this live or in a recording have gotten a copy of the handout from your teacher so you can follow along. If you didn't, don't worry about it. This video, like I said, is going to be recorded and available on YouTube at a later date. So follow along now as best you can. And if you want copies of the problems that I'll be working with as I go through this particular topic, please feel free to ask your teacher for the link to that folder. So what I'm going to do is I'm going to spend a little bit of time talking about two specific topics, Euler's method and logistic growth functions, or more specifically, logistic differential equations. When we deal with these two functions, these two different topics are BC only topics. They're not on the AB exam, but they fall under a bigger umbrella of differential equations. So I'm going to start sharing my screen so I can show you what I'm working on. Okay, so hopefully you see this, and you should see a first page. It says Euler's method and logistic differential equations. So under the big umbrella of differential equations, there includes several topics that are both on the AP Calculus AB and BC exam. Let's go over a few of those. So what you should know, and this covers more than just the two topics I was talking about, you should know how to verify solutions to differential equations. So if it says something like y plus y prime equals 25, you should be able to put in your function y, the solution, and your y prime into the equation so that it all works out. You should know how to do geometric interpretations of differential equations using slope fields. So this is your geometric approach to solving a differential equation. It gives you a general solution unless you have an initial condition, and then you can follow the slope field to get a picture of what an estimate better of what the actual function would look like. Numerical solution of differential equations using Euler's method. Now, Euler's method is actually a BC only topic, right? Geometric interpretations of differential equations, slope fields, and the one before it are fair game for the AB exam. We're going to talk about Euler's method today. Solving separable differential equations and using them in modeling. So this should be a prime. And then that includes functions of this form y prime equals ky and the exponential growth and decay functions. Again, these type of functions are on both the AB and the BC exam. And lastly, under this general area of differential equations, the BC only topic of solving logistic differential equations and using them in modeling. So I'm going to start with Euler's method, which is a numerical solution. So if you think about it, you have to be able to experience differential equations numerically using Euler's method, geometrically using slope fields, and algebraically by actually solving them using the method of separating variables. So quickly going over the steps for Euler's method, right? This is just a general outline of what you need to do. There are a lot of different ways to do this. Some teachers use tables, some people just write equations. I started out doing tables and then switched to equations after seeing how things were graded on the AP exam, for one thing, and because it tied in easily with writing equations with tangent lines. I thought to start writing them as equations. So you have the differential equations. You want to solve for dy. You want to substitute the values that you have of x and y and dx to calculate a new dy. And then you find the new y value by adding dy to the old value of y. Let me kind of slow this a little bit, right? So you start out with some initial point. Let's say it's 1, 2. then that's your x and y. And if dx is, say, 0.5, right, then to find the value for the y value for the new x value, which would be 1.5, right, because that'd be x plus dx, you have to figure out what dy is, because dy is how much you change. So in order to find the dy, you have to have an expression for dy dx, substitute those values in to get that new dy, and then add it to the previous value of y to get the y value that goes with this next x value, and then you keep going until you get the y for the value of x you're looking for. Maybe it'll be a little bit easier if we look at an example. Right? So hopefully you can see this. I can see it just fine. I'll show it in a bigger print so you can see it a little clearer. So this is from the AP Calculus BC exam from 2013, and this is problem number 5. And the reason I have part B boxed is that that's really the only part I'm going to look at, the Eulers method parts. The other parts are important, but not relevant to the topic at hand. So we have the differential equation dy dx is equal to y squared times 2x plus 2. And y equals f of x is the particular solution with an initial condition f of 0 equals -1. In part B, they want us to use Euler's method starting at x equals 0 with 2 steps of equal size to approximate f of 1/2. Well, the first thing I need to do is, well, if I'm taking 2 steps of equal size and I'm starting with an x value of 0 and I'm ending with an x value of 1/2, then halfway between those would be 1/4, and that way I'm taking 2 steps of equal size. So since this expression up here is dy dx, that means that dy is equal to y squared times 2x plus 2 times dx, right? So we're going to have to calculate this new dy every time. So I like to think of it as writing an equation for a tangent line. You need to find the y value that is approximately equal to the y value that you have, which is -1, plus the slope of the line, which would be y squared, so -1 squared times 2 times 0 plus 2. Right? That gives you the slope of the line. And then you're going to multiply that times, well, basically dx, right? Because it'd be 0 minus 1/4. Notice that dx in this case, how far it is from here to here, is 1/4. So times 1/4, right? That's going to give me my new y value. So this is 2 times 1, which is 2, times 1/4, which is 2/4, a half. So my new y coordinate is -1 plus a half, or -1/2. So now we're assuming that we have a point 0, -1/2, which would be, oh, not 0, sorry, 1/4 -1/2, which would be my first estimate. Now I need to do the whole thing again, right? So starting with the point 1/4 -1/2, my new y coordinate would be -1, oops, sorry, -1/2, because that's the new, that's now this y value, right? Think of this as y coordinate plus slope times delta x, a change in x. So the y coordinate now is -1/2, plus the slope, which would be -1/2 squared times 2 times 1/4 plus 2. That would give me the slope of this line times 1/4. This is my second iteration. I'm going to go ahead and simplify this a little bit. -1/2 plus 1/4 times 2.5. So what's that? 5 halves times 1/4. So this is going to be equal to negative 1/2 plus 5 over 32. So negative 16. So my final point would be 1/2, comma, multiplying, changing negative 1/2 to have a denominator 32, multiply top and bottom by 16, negative 11 over 32. Right? So that means that f of 1/2 is approximately negative 11 over 32. So on the AP exam, a problem like this is usually 2 points. They usually look for the 2 iterations and see if you have the answer. You have to be careful when using tables. We're okay with tables. The readers will grade tables. However, if you use a table, you have to be careful to label the columns correctly so that they can follow along. And you need to show enough work to show how you're getting the Y values. Since you have to show the work anyway, I just started to move away from using the tables altogether, because without the supporting work, you're not going to get full credit for using Euler's method. The other thing I want to caution you is here, right? Notice that I wrote approximately equal to. Now, if I had just said negative 1/2 plus 5 over 32 was my answer and boxed that or underlined it, that would be fine. But if I say that f of 1/2 is equal to negative 11 over 32, I've made a mistake, right? This is clearly an approximation. F of 1/2 probably doesn't equal negative 11 over 32. And it's the kind of thing that might risk you losing a point on the AP exam because you said use what's essentially bad notation. So that's one example. I'm going to look at a second one. This is from 2012 on the AP Calculus BC exam, and this is number 4. And we're going to just look at part C. Again, it's the only part that has anything to do with Euler's method. So we've defined a function f to be twice differentiable. We've given it 2 initial conditions, actually, that f of 1 is 15 and f double prime of 1 is 20. Values of f prime are given in the table. And in part C, they want us to use Euler's method starting at x equals 1 with 2 steps of equal size to approximate f of 1.4. So again, if I'm starting at f of x equals 1 and I'm going to x equals 1.4, right? I'm starting at x equals 1 and I'm ending up at x equals 1.4. Halfway between them is 1.2. That'll be 1, 2 steps. A lot of times, especially on free response, the question will be in 2 steps. So keep that in mind, that it doesn't necessarily have to be 2 steps, but a lot of times it is. So when x equals 1, y is equal to, well, it's up there in the top of the problem, 15. Okay. It's right here. So finding my new value would require me to go, okay, let's pretend I'm writing an equation for a line. Y equals the y coordinate we know, 15, plus dy dx, which at f of 1, that'd be f prime of 1, times dx, which, as you can tell here, I'm going up by 2/10, which is 0.2. I look around and I notice, oh, up here in the table, I actually have f prime of 1. It's 8. So it's really approximately, right? This is 15 plus 8 times 0.2. 8 times 0.2. So let me move over so you can see that. Is 1.6. So my y value here is 15 plus 1.6, approximately 16.6. Right? So 16.6 is going to go with 1.2. I need the y value for 1.4, at least the approximate y value for 1.4. So I go, okay, well, the new value that I want is going to be about the last value, 16.6, plus f prime of 1.2 times dx, which is 0.2. If it helps, remember that y is going to be equal to the old y plus f prime of x dx. So I look back in the table over here and I go, oh, here we go. I have f prime of 1.2. It's 12. So this is going to be equal to, maybe I should write it down here, 16.6 plus 12 times 0.2. And 12 times 0.2 is 2.4. So that means my new y value is going to be 18, actually 19. So f of 1.4 is approximately 19. Now, one of the things that readers have been picky about in the past, at least, is actually noting that what the answer is, right? If I just left it like this, it's not necessarily clear to the reader what the answer is. We could kind of go with maybe it's down at the bottom, but I wrote a lot of y's. So making a point of stating the answer or circling the answer or underlining the answer is actually a good thing in this type of problem. I'll do one more example of Euler's method before moving on. And in this one's from 2010, and it's from number 5 on the AP Calculus BC exam. We have a new differential equation, dy dx is equal to 1 minus y. And they tell us the stuff about the particular solution. This is pretty much the language that they're going to use every time. That f of 1 is equal to 0. And in part A, the only part we're going to be worried about right now, we want to use Euler's method starting at 1 and go 2 equal sides to approximate f of 0. Notice we're going backwards. So that's an important note as we use Euler's method to solve this problem. So since I'm doing part A, right? I'm starting at x equals 1. I'm ending at x equals 0. Halfway between them, I wrote that backwards, I don't know why, is x equals 0.5. So this really means that dx, since my values are going down, is a negative number. And I hope that makes sense as to why dx has to be negative, since I'm going from a greater value of x to a smaller value of x. I'm going down by negative 0.5. I'm going down by 0.5, subtracting 0.5 from the x value. So when x equals 1, y is equal to 0. They told me that up there. So my new y value will be my old y value plus dy dx, which would be 1 minus my old y value, times dx, which would be negative 0.5. So my new y value is actually negative 0.5. Easy enough. So when x is 0.5, y is about negative 0.5. That's one iteration. My next iteration, I'm going to go, okay, well, my next iteration, and if you find all these y's confusing, you might want to tag them, right? This is y, this is to phi y1, and that's y1, the one that goes with 0.5. Now I'm working on my second y. Okay, so if it helps to follow me that way, you can do that. That's going to be the previous y coordinate, which is 0.5, plus dy dx, which is 1 minus y, so 1 minus a negative 0.5, times dx, which is negative 0.5, right? Minus the negative will give me a plus. So this is going to be equal to negative 0.5 plus 1.5 times negative 0.5. And let's see, half of 1.5, that'd be 0.725. Yeah. So this will be negative 0.5 plus negative 0.72525, right? Multiply that by 2, 14. No, I did that wrong. It's negative 0.75. Right, double that, I get 1.5, and it's negative because this was negative 0.5 to begin with, which is negative 1.25. So my answer here, and it's a good thing I meant my answer because I'm almost running out of space, is f of 0 is approximately negative 1.25. So as a reminder, they're basically going to be looking for two steps, right? So it's important to show that there are two steps. One step to get y1 and another step to get y2, in this case, labeling them that way. And that usually is a point. And then the 1 point for two steps. And then the approximation itself is usually a point. Right? So out of the 9 points, this is probably 2. Now, the reason I'm being extra careful in saying things like probably and maybe and could be is that these things could change. This is from my experience as being a reader, but things are always changing, and so there's no hard and fast rule that things are going to stay this way. So let's move on from Euler's method and start talking about logistic growth. So this is the logistic differential equation where k and m are constants and y is a function of x. So dy dx is equal to ky times m minus y. Now, you may not necessarily see it in this form, but what we're saying is it can be written in this form. So you may have to factor something or multiply something or do something like that to get it in the form that you want, but it is possible for it to be written as a constant times y times m minus y. I think a good way to remember this is that this is a factored quadratic with y equals 0 as one of the roots. Now this number, m, I use an m, you could use whatever letter you like, but that constant is called the carrying capacity. So a lot of times, logistic differential equations are used to, sometimes logistic differential equations are used to describe populations. For example, bacteria in a petri dish, fish in a pond, deer in a forest, where there is a maximum number of deer, fish, bacteria that can be sustained in that particular environment. That maximum number is called the carrying capacity, right? This fish tank will only hold 125 fish. What happens if you start to go over the carrying capacity is that it can't carry that many fish. So if you put in 126 fish, one of those 126 fishes is going to die to bring it back to 125. So that's kind of what the context is usually for logistic growth equations. Now, when you look at your k value in the equation that I showed you before, and I'll go back to it in a moment, that is a constant of proportion. So kind of like solving dy dx is equal to ky, which leads to an exponential growth equation where you have a constant of proportionality. Here you also have a constant of proportionality. So it's important to see the similarities as well as the differences between the types of differential equations. Let me go back to sharing. So the logistic function, that is, if you solve this differential equation, and no, I hope you notice that if you started to solve this, well, let me take a moment and talk to you a little bit about what it would take to solve this, right? If you were going to attempt to solve a differential equation looking like this, and because I know constants bother people, I'm just going to make up some numbers. So I am making up numbers. So let's say dy dx is equal to, let's say k is 3, so 3y times, let's say m is 7 minus y. Okay? And you wanted to solve this differential equation for y. This is totally something that they could ask you to do on the AP exam. I don't think they will, because it just takes a lot of steps to do it. So dy dx is equal to 3y. I'm going to separate the variables, right? The only method that you have to know for solving a differential equation by hand on the AP Calculus exam, AB or BC, is the method of separating variables. And this is going to be easy to separate. Some people think of this as cross multiplication. Other people think of it in different ways. This is how I've separated. I like to leave the constant over there on the right. I don't know where I picked up that habit, but somewhere along the way, I picked that habit. Well, when you go to integrate both sides of this equation, we know what's going to happen over here, right? That's just a constant, pretty easy. But notice that this is actually the product of two monomial factors. So what we're really going to want to do is we're going to want to do do integration using partial fractions. Now, I actually talked about this type of thing in a previous video. Go back and watch it on YouTube. You can find the link on AdvanceKentucky.com or on AdvanceKentucky's YouTube page if you want to go over this in detail. I'm just going to do this really quickly. I think I'm going to do this really quickly. Why does that feel right? You know what? I'm not going to do it pretty quickly because I feel like I'm doing it wrong. So let's see, a times 7 minus y plus by is equal to y times is equal to 1, right? So if y is 0, that means by is equal to y is 7. Kind of slow today. 7b equals 1, so b is 1/7. I don't know why I wasn't feeling that was right, but I caught myself. Over here, I'm just going to go ahead and integrate 3, right? That's pretty easy to do. But you get the gist. This is something that you can solve, right? This is something that using your skills as a BC student, you could solve. I'm not going to take the time to do that right now, but you get the idea. Well, what I'm saying here is the solution of this differential equation can be written in this form. Remember that solutions to differential equations are functions. And you could rewrite this so that the carrying capacity is in the numerator. There's some magical constant A that you can determine by using the initial condition. And this K and that K are the same number. So to go through all the steps to get that, maybe I'll do that a little later at the end of the video or something, depending on how much time I have left. So let's look at a logistic equation. I'm going to show you a slope field. So here's a slope field for the logistic function 2y times 3 minus y. And I've gone ahead and shown you a particular solution given the initial condition for 1. So what I hope you notice is this. Right? Along the horizontal axis is a horizontal asymptote, i.e. when y is 0. And up here, and hopefully you can see that that's 1, so that would make this 2, and that 3. At y equals 3, ooh, when y is 3, it would make that whole thing 0. I have another horizontal asymptote. So I can tell what the asymptotes are by just finding the zeros of the differential equation. Y equals 0, y equals 3. A common question that gets asked a lot is, well, what happens if I start below the x-axis or above the x-axis? Well, what happens is, let's say we start at, I don't know, the point 0, 4, right? That's 3, so here's 0, 4. If I follow my slope field, first this way, and then that way, and this will continue all the way out. What happens is that that y drops down to the carrying capacity, kind of like those fish I was talking about a few minutes ago. And likewise, if I start at some random point down here, if I follow the slope field, it will eventually have a horizontal asymptote at the x-axis. So those two values are keeping the population in between. Besides, it doesn't really make sense for y to be negative if y is representing something like a population. It doesn't have to represent a population, but that's what it's usually representing. Now here's my point 4, 1. And notice that at this point, if I go out to the left, I go horizontal axis, and I go up to the right. But there's also a change in concavity. It's not really at the point 4, 1, though. Right? From about here over, oh, my hand's covering that up. Let's do it this way, right? From about here over, my graph is concave up. And from about here over, my graph is concave down. In fact, remember this is 3. If I go through right about here, well, actually not here, maybe a little lower here. That point would be at a point of inflection, about halfway between the 3 and the 0. In other words, the carrying capacity. The reason I'm pointing out this point of inflection is that that point of inflection is when dy dx is changing the fastest, right? That's when this curve is the steepest. That's when dy dx is changing the fastest. So, in other words, the place where the function is changing the fastest is always going to be at half the carrying capacity. Now, luckily for you, you don't have to prove that. You just have to know that. So having said that, and ignoring the blue that leaked through on the other side of my page, I didn't really plan for it to come out two-sided, it just did. Let's look at this function, right? So this is a slope field for dy dx equals y over 5 times 1 minus y over 12. You're probably thinking to yourself, that doesn't look like a logistic differential equation. Well, sure. But I could easily rewrite this differential equation as dy dx equals 12y, or 12/5 y, times 12. Sorry about that. I'm getting myself a little confused here. No. Well, I can easily factor out 1/12. Let me do it that way. So it's 1 over 5 times 12, that's a 12y, equals 12 minus y. That's what I was trying to get to. And if I get it this way, then this is the k, and that is the m. So the carrying capacity is 12, and the constant of proportionality is k. And if I look at my slope field, notice that that says 15 up there. 15, 13, 14, 12, right about in here is 12, And notice that it looks like it's going to do a horizontal asymptote. It's cut off a little bit, but it's pretty much looking like it's going to do that. And it has another horizontal asymptote down here at the x-axis. So since the carrying capacity is 12, that would mean that it's increasing the fastest at the point of inflection, which happens to be halfway between 0 and 12, or at 6, half the carrying capacity. So hopefully some of that will go through, and we'll look at an example. The example we're going to look at is from 2006. It was number 5 on the AP Calculus BC exam. Let f be the function with f of 4 equals 1, such that all points x, y on the graph satisfy the differential equation. dy dx equals 2y times 3 minus x. Let g be the function with g of 4 equals 1, such that all points x, y on the graph satisfy the logistic equation dy dx is equal to 2y times 3 minus y. Part A says find y equals f of x. And part B, the part that I have boxed, is the part that's asking about the differential equation. Now, when you look at part A, it's referring to this differential equation. And even though they look very similar, there is a significant difference between this differential equation and that one. This differential equation is logistic, ky times m minus y. This is logistic. The key here to knowing that it's a logistic differential equation, other than the form, is that it's a function of y only, no x's, and it's quadratic. That might be helpful to you to remember that. This one has both x's and y's in it, so it's not a logistic differential equation. So just for the fun of it, what I'm going to do is I'm going to do this whole problem. I only boxed part B and C, but I just finished grading some sample exams, and some of you out there need a quick reminder on how to solve variable separable differential equations. So let's start with the differential equation right here, dy dx equals 2y 3 minus x, and part A says find f of x. This is for part A. dy dx is equal to 2y times 3 minus x. And we have the initial condition that f of 4 is equal to 1. Okay, so separating the variables, dy over y is equal to 2 times 3 minus x dx. Again, I like to keep the constants on the right, just because I don't know why I necessarily have that preference, but I do. Taking the antiderivative of both sides, ln absolute value of y is equal to, if I multiply this out, right, this is 2 times 3x minus x squared over 2 plus a constant. So I'm going to go ahead and multiply the 2 through on the right side. 6x minus x squared plus a constant. I'm now going to transform this function from a logarithmic equation to an exponential. Some people go ahead and plug the initial condition at this point. I actually prefer to solve for y first and then plug it in. It really doesn't matter in terms of what's happening on the AP exam in terms of scoring. So y is equal to some constant times e to the 6x minus x squared. So this plus c is going to make it be e to the c, which could be positive or negative. So I just rewrite that as a. I choose to use a because I like a, and I like for those letters to look different, but I don't have to. Now I'm going to go ahead and plug in my initial condition, right? So y is 1 when a times e to the 24 minus 16. So 24 minus 16 is 8. So e to the minus 8 is equal to a. And therefore my equation is y equals e to the minus 8 times e to the 6 x minus x squared. You can leave it like that. I'm going to just write e once. So e to the 6x minus x squared minus 8 is my solution. Differential equations like this are usually worth 5 or 6 points. I don't remember what the rubric is, but they usually go pretty similarly. You get 1 point usually for separating the variables correctly. If you make a mistake in separating the variables, how bad the mistake is how many points you're going to be worth. You're definitely not going to get the answer point. But if you try to do something other than using multiplication and division, you're going to be in big trouble. There are two antiderivatives here, and one of them involves ln. I'm going to say that there were probably 2 antiderivative points, but there could be just one. This is not a hard antiderivative, so it might be just one for both. What I would say is that's really important is don't forget to put the absolute value of y, or if you don't put it, put some notation over somewhere why you're not putting it. So put it. The absolute value of y around the natural log, and you get 1 point just for the constant of integration. So right now, I've already earned 4 of presumably 6 points. 1 point for plugging in your initial condition. Notice that it's not for solving it, it's for just plugging in this case, 4 for x and 1 for y. And then 1 point for the correct answer. Now, 5 points, they may have given 1 point for the antiderivatives and everything else is the same. Or they could make it 5 points by giving 1 point. I recently saw this on an exam where the initial condition and the substitution were worth 1 point together. But this is usually 1 or 2 points, definitely 1 point here. This is the 6.1. This would be 1 point. And you only get this last point for the correct answer. You can't get it for anything else. If I stopped up here a line above, I would still have my 1 point. That last point. Here, I don't get it. I have to express it as y as a function of x to get that last point. Okay, so that's a quick review of solving variable separable differential equation. Now, when I look back here at part B, we start talking about function g all of a sudden. Given that g of 4 is 1, find the limit as x approaches infinity of g, and the limit as x approaches infinity of g prime. Well, if you remember that slope field, those 2 examples, the horizontal asymptotes were at the carrying capacity and at 0. So the limit as x approaches infinity of g of x is going to be equal to the carrying capacity. So this limit, let me make sure I understand what's on the other side of this. So this limit is equal to 3 because that's the carrying capacity. Sorry about that. And the second part is the limit as x approaches infinity of g prime. Well, what's the slope of a horizontal line? Isn't it 0? So the limit as x approaches infinity of g prime, well, as x goes to infinity, y goes to 3, right? If I put 3 in here for y, I clearly get 0. So the limit as x approaches infinity of g prime is 0. Now notice this note that it had here, and this was actually on the AP exam. It is not necessary to solve for g of x or to show your work. There's really no work to show here. So you just had to write the values of the 2 limits. Now you can't just write 3 and 0. They have to be labeled. But other than that, that's all the work that you would have to show for part B. In part C, for what value of y does the graph of g have a point of inflection, and you find the slope of the point g at the point of inflection. Remember I talked to you about point of inflection? Where was it? The point of inflection was halfway between 0 and the carrying capacity. In other words, it's half the carrying capacity. So G, this is part C, has a point of inflection when y equals 3/2, half of 3. Find the slope of the graph of g at the point of inflection. Well, the slope of the graph is dy dx. So we want to find dy dx with y is equal to 3/2. Oh, I wrote that mighty big. That should be down there somewhere. Oh, and you can't see that, can you? There you go. And that's going to be 2 times 3/2 times 3 minus 3/2. So that's 3 times 3/2 or 9/2. So what we're looking at here is these are BC topics, but if you really know the differential equations well, you don't have to do very much work. We know that the limit as x approaches to infinity of g of x because in our slope field for logistic growth equation, we had a horizontal asymptote at the carrying capacity when, in this case, when y is 3. And the limit as x approaches infinity of g prime of x, well, if I put this value 3, which is really when it happens when x is going to infinity and y is going to 3. If I put the value of 3 in here because y is going to 3, then dy dx is going to be going to 0. So I hope that I didn't go too fast for you. It's pretty simple enough. These were pretty much worth 2 points for each part, right? So if I say that, that means that part A was probably worth 5 points. I could look it up, but we'll just go on my very educated guess here. 1 point for that limit, 1 point for that limit, 1 point for the y value, and 1 point for dy dx. So let's go on to another example. Right? And remember, all of these examples are in the handout. So if you have the handout, you can go ahead and just make notes and write things on here. Oh, by the way, did you notice something about that differential equation on the previous problem? Like that slope field I showed you was this differential equation. I wonder if that was on purpose. So 2004 BC5, this is from the 2004 AP Calculus BC exam. It was number 5. Notice that all of the problems I'm doing also were in no calculator portions. Right? This is generally going to be the case that they're going to be in no calculator. There are some calculators that can solve differential equations easily, and that's giving an unfair advantage. So most questions like this will probably be on the no calculator part, as all of the examples I've shown you so far have been. So we told you it was a logistic differential equation, even though it didn't look like one. Oh, wait, that looks familiar. Didn't I just show you a slope field of that differential equation? It's like I knew what was coming. I'm going to rewrite this, though. 5 times 12 is 60. I remember that now. So it looks like k times the y value times m minus the y value. So now we know that m is 12. Part A, if p of 0 equals 3, what's the limit as t goes to 0 of p is? You know what? It doesn't matter what p of 0 is. It doesn't matter where we start, because it'll always come down to the carrying capacity. So this limit is actually equal to 12. I'm just going to write it right there. On the real exam, you'd have to write it in the space, but I'm just going to write it right here. If p of 0 equals 20, what's the limit? The limit's the same, right? The carrying capacity is the carrying capacity no matter what the initial value was. So this limit is also 12. And for part B, if p of 0 is equal to 3, for what value of p is the population growing the fastest? Again, it doesn't matter where I start. The population is growing the fastest halfway between 0 and the carrying capacity. In other words, when P is equal to 6. Okay? That's all there is to that. It's kind of scary how easy that is, right? You just have to know about carrying capacity, about ideas what the slope field and therefore the solution of the differential equation looks like to be able to answer these questions pretty quickly. They were not looking for any work per se. You couldn't just write the number 12, of course. You had to write the limit as t approaches infinity. If P of t is equal to 12, use good notation. But that's it. That's all you need to do. I think that's 3 points. So I'm looking at a part C where I'm solving a differential equation, and then at part D where I'm finding a limit. So notice that this equation that they're asking me to solve is actually not logistic. That's a T right there. So even though it looks very much like this one, by changing that to a value T, we are now no longer looking at a logistic differential equation, which is good because in this particular case, we would not need to use partial fractions to actually solve for the function y of t. I'm not going to go through the steps here. I'm just going to move on a little bit to multiple choice. So if you continue moving on to the multiple choice questions, again, this is a mixture of questions that have appeared on previous AP exams. I don't remember which ones are which, but I have answers in the handout. So if you actually download the handout, and most of them will also tell you which exam this was from. So in number 1, we're given the point y1 equals -3 and dy dx. What's the approximation of y equals 2 if Euler's method is used with a step size of 0.5, starting at x equals 1? So we actually have 3 x values, right? We have 1, we have 1.5, and we have 2. We're basically taking 2 steps. I'm going to write this as a table so you get an idea of how you can do that. When x is 1, y is -3. And now to find the new y value, I need to find dy. Well, dy is really dy dx times dx. And in this case, the step size is dx. So 2x plus y, so 2 times 1 plus -3 times dx, which is 0.5. This could have been on the calculator portion. There's a lot of decimals, or it might not have been. This is a -0.9 times 0.5 is -0.45, so this is -3.45. I hope I did that arithmetic in my head correctly. And then we go on with the rest of the steps, right? So I'm thinking that if I do this next one, I get 2 times a -3.45, that's -6.9, minus 3, that's -9.9, times 0.5, that is 4.4525, and then I add the numbers together. Anyway, you get the idea. Let me see. I'll go back and see what the answer is. I'm going to look it up because I have the handout with me. The answer to this one is D, -3.75. Okay. So notice that I added this dy to the y value to get the new y value. And then I do the same step again to get the next y value. Okay. So here, so number 1 is D. Really starting to feel like I should work that out, but I don't want to show you. I don't want to show you bad arithmetic, so I'm not going to go ahead and do that. And my time's running low, and I want to finish doing this. So, which of the following differential equations for a population P could model the logistic growth function in the figure above? Well, notice that this function has a carrying capacity of 200. So, since there's a carrying capacity of 200, we're thinking K times P times 200 minus P is my differential equation. Some constant times this. I look down here and notice that, well, these are actually multiplied out, so that's not a big deal. I can multiply this out. K times 200p minus kp squared. So I'm going to look for something in that form. So I know, for example, that it can't be E, that's not the right form, or D, that's not the right form, or C, that's not the right form. So I'm down between these two. Okay? The way I'm going to pick between the two is I'm going to plug 200 in. I actually think it's B, but I'm going to plug 200 in. Right? Because if I plug 200 in and get 0, that's what? That's the carrying capacity. So this is 40 minus 0.001 times 200 squared, which is 40000. And I take off 1, 2, 3, 4 zeros, 1, 2, 3, 4, 0, 0, 1. Take off 3 zeros, 1, 0. So it's 40 minus 40, which is 0. So I'm thinking the answer is probably A. I'm pretty sure that if I plug this in, if I change this 0.2 to a 0.1, it doesn't work. So A. Still with me? I only have 3 more problems to do, and then we'll be done. So let's look at, let's not look at it there because now it's all squishy because I wrote on top of it. Let's look at number 3. Like this is from the handout. Okay. So number 3, the population P of T of a species satisfies the logistic differential equation dp dt equals P times 2 minus P over 5,000, where the initial population P of 0 is 3,000. What's the limit as T goes to infinity of P of T? Well, we know that the carrying capacity will make this value equal to 0. I'm not even going to bother to put that in there. Since that's 5,000, if P is 10,000, then I get 2 minus 2, which is 0. So the answer must be E. Did I go too fast for you? If I put 10,000 in here for P, 10,000 divided by 5,000 is 2, right? 2 minus 2 is 0. That means that the carrying capacity must be 10,000. If you're not convinced, you could factor out 1 over 5,000 and get it to look like the form that we're familiar with. dp dt is equal to 1 over 5,000 P times 10,000 minus P. I'm still getting 10,000. Let's look at the rest of the multiple choice questions. In number 4, let y equals f of x be the solution to a differential equation that's given this f. I don't know why this f is dragged off to the side, but that should be f of 1 equals 2. And what's the approximation for f of 2? If we start at 1, we do Euler's method. We've done this a couple of times now. Let me go down here. X equals 1, x equals 1.5, x equals 2. Step size is 0.5, right? So when x is equal to 1, y is equal to 2. When x is equal to 1.5, y is going to be about 2 plus dy dx, which is x plus y, 1 plus 2 times dx, which is the step size, 0.5. That's 3 times 0.5. So this is equal to 3.5, right? 2 plus 1.5. And then that means that that's my new y value. So that's y1 if you want to call it that. So my next y value is going to be my previous y value, 3.5, plus the dy dx. In this case, it would be 1.5 plus 3.5 times delta x, which is 0.5. So that's 3.5 plus, this is 5 times 0.5. Half of 5 is 2.5. 2.5 plus 3.5 is 6. So the answer is 6C. And the last differential equation I have to deal with is actually logistic. The number of moose in a national park is modeled by the function m that satisfies the logistic differential equation, where time t is in years and m of 0 is equal to 50. What's the limit as t goes to infinity of m of t? It's the carrying capacity. And looking at what makes this factor 0, that must be 200. If I want, I could factor out 1 over 200. That would change what's in here if I factor out 1 over 200 to 200 minus m. So that's another way of confirming that that answer is correct. So ooh, I'm getting some glare. I should have closed the window. So that's the end of the handout and really the end of my talk. I'm going to spend a few minutes now for anybody who's interested in me finishing that problem that I started, where I was showing folks how to solve that differential equation. I feel like I need to finish it just because I hate leaving things unfinished. As you're looking at, as we're going through this and getting ready to look at this last problem, I have one more thing to say. And that is, I'm going to check my Twitter as soon as I get off of this. What is this? Get off this video. So once I finish live streaming, I'm going to check Twitter to see if you have any questions, and I'll tweet you back, I promise. You can ask me questions now. You can ask me questions later. You can ask me questions when you really watch this video. The questions, you can either tweet me directly at Monique Morton, at Monique_Morton. You can use the hashtag AskMoniqueKY. You could have used the chat, but I didn't, since I was mostly using the document camera, I wouldn't be able to do that. So if you're watching these videos and you'd like to see my next live stream, the next topic for AP Calculus BC is parametrics and vectors on Monday, April 18th at 6:30 p.m. Eastern Daylight Time. So right now, if you're done with me, you can go ahead and go forth and conquer. I am going to finish this problem because the fact that I haven't finished it is kind of bothering me. So if you're watching me, to finish this problem, I'm going to check my other y value for a second here. So if y is 0, then a times 7 is equal to 1, and a is 1/7. So I'm glad I checked that because I need to correct that right away. Now I know immediately what I did wrong, which is really why I stopped the problem, because I knew my constants weren't right. And now they match, and I feel better. So what I'm going to do to finish this off, so here's the beginning, right? dy dx is equal to 3y times 7 minus y. It's a logistic differential equation. I separated the variables. I'm taking antiderivatives. I'm decomposing this fraction into partial fractions. These are my numerators for my partial fractions. This is the antiderivative of the left side and the constant of integration. And these are the antiderivatives of, well, that's the right side of the left side. What I'm going to do now is I'm going to go ahead and combine this into one logarithm before I do anything else. So if I combine this into one logarithm, I can write this as 1/7 ln absolute value of y over 7 minus y, and that's going to be equal to 3x plus c. I'm going to go ahead and multiply by 7. Ln absolute value of y over 7 minus y is equal to 21x. I'm just going to write c. I'm not going to say c2 or 7c or anything like that. C is just a placeholder for a constant. Now exponentiating y over 7 minus y is equal to some constant times e to the 21x. This is as far as I can go without an initial condition. If I had an initial condition, I wonder if I could make something up that would make sense. I'm kind of scared. Let's say that y of 0 is 5. Something easy to do here. So if y of 0 is 5, I'm going to put 5 in for y. And 0 in for x, so that's a. So a is going to be equal to 5 halves. And once I get to this point, I'm pretty much going to need to do some algebra. So y over 7 minus y is equal to 5 halves e to the 21x. Solving this equation for y, because I'm not done until I solve it for y equals 35 halves e to the 21x minus y times 5 halves e to the 21x. So this is y times 1 minus 5 halves plus adding both sides as e to the 21x is equal to 35 halves e to the 21x. And finally, y is equal to 35 halves e to the 21x divided by 1 plus 5 halves e to the 21x. A little more manipulation would get it into the form that I mentioned before, right? If I really want this to be a 7 up here, I could probably manipulate this by dividing by this number in the numerator, and that will change some things around, but I'm not going to bother, or actually divide by what's in the denominator, right? Okay, I said it, so now I feel like I have to do it. So y equals, if I divide this by that, that'll give me 7. Over, if I divide this by that, that'll give me 5 halves e to the minus 21x. Actually, it gives me 2/5 plus 1. So there we go. All right, I feel better now that I got that done. Hope to see you next week. We'll read the next one on Monday. We'll have another one on Wednesday. And if you have any questions, please feel free to tweet me. Bye.